In this video, we're going to discuss section 2.2, equilibrium solutions and their stability. This section is going to focus on what's known as autonomous DEs, and those are a very particular type of DE that make them slightly easier to solve. So an autonomous first order DE is a first order DE that is independent of the variable t. So that is the takeaway here. We are assuming that t is the independent variable and x is the dependent variable. So what we see here is on the right-hand side, a function that depends only on x and that independent variable t is missing. We call the roots of the function f of x within this autonomous DE critical points. This term should be familiar to you from the calculus series. If you'll recall, when we're working on optimization and finding maxima and minima of single variable functions, we take the first derivative, we set it equal to 0, and we solve for the roots of that derivative. And that's precisely what we're doing here. You'll notice that the derivative is on the left-hand side, and then we're setting that derivative function equal to 0 and solving for x. All right, and we're calling those x values critical points. If we found a critical point, x equals c, then we call the constant solution x of t equals c an equilibrium solution. So notice this notation here, this kind of triple equal sign, that's not a typo. When I have x equals c, this means a particular value for x. We have solved for x and we found for c. In this triple equals notation, what I mean here is that the x of t as a function dependent on t is just the equilibrium or the constant solution c. So that triple equals is saying that this is functional notation, not an assignment of a value. What we'd like to do in this section is classify these equilibrium solutions based on their stability. So we have a definition here. Intuitively speaking, a critical point C is stable if nearby solution curves converge to the equilibrium solution x of t equals c as t increases. So what this means is as your independent variable is increasing, your your solution curves are tending toward that equilibrium solution. We are unstable if a nearby solution curve diverges away from that stability or from that critical point or that equilibrium solution. And then we have something kind of in between. A critical point is semi-stable if these solution curves converge on one side and diverge away from that equilibrium solution on the other. So we have a tool that's going to aid us in determining the stability of critical points, and that tool is called a phase diagram. It's secretly just the first derivative test from Calculus 1. So we have a phase diagram is a diagram composed of a line segment containing the plotted critical points of a given autonomous first order DE, as well as arrows indicating the sign of the derivative. The stability of the critical points can be determined using the phase diagram. So let's just sketch an idea of what these phase diagrams are going to look like. We're going to have a portion of the real number line here. And keep in mind that your number line is in terms of x in this case. So rather than t, I should write x. We're finding x values. And then we want to plot our critical points. So let's suppose that we have 3 critical points, x1, x2, x3. And we would like to pick test points in between. So I'm going to color those test points. I'm going to call them x sub a, x sub b, x sub c, and x sub d. All right, so all these are our real numbers in between each of these intervals on the x-axis. All right, and what we're going to do is we're going to plug those test points into f of x, or the derivative, and identify whether it's positive. So I'm going to plug x sub a through x sub d into dx dt equals f of x, and note the sign. So is it positive or is it negative? It's certainly not going to be 0 because we found those zeros and those are x1 and x2. All right, so we're going to note those things and I'm just going to make up values. Let's suppose that f of x is positive, then it's negative, then it stays negative, and then it's positive. And I'm just making up these values because we don't actually have a problem here. Um, then what you want to do is you want to draw arrows on that portion of the number line that point either in the positive or negative direction, depending on whether your derivative is positive or negative. So I'm going to maybe color these so they stand out. Let's do them in blue. So since this derivative was positive, I want my arrows pointing in the positive direction. Then they were negative here. And I want it pointing negative in this entire interval. So I'm drawing two arrows, one towards x1 and one away from x2. It continues to be negative in this third portion. So I'm having my arrows point to the left, which is the negative x-axis. And then finally, our derivative is positive, so I want those arrows pointing forward. All right, so then let's take a look here. At x1, you can see the arrows are pointing towards x1. That means that the solution curves will converge to x1. So we would classify x1 as a stable critical point. Let's look at x2. From the left, we're diverging away from x2, and from the right, we're converging toward us. So that would be a semi-stable critical point. And at x3 here, both of our arrows are pointing away from x3. So that means our solution curves are diverging away from it. So that would be unstable. So this is just a general diagram of how you're going to set up these phase diagrams, but they're very quick and very efficient at classifying the stability of critical points. All right, so now we're just going to move forward with several examples here, and we have quite a hefty set of directions here. So for these examples, solve the equation f of x equals 0 to find the critical points. Then analyze the sign of f of x to determine whether the critical point is stable, unstable, or semi-stable, as it may be, and construct the corresponding phase diagram. Next, you want to solve the differential equation explicitly for x of t in terms of t. I want to emphasize here explicitly. We want to solve for x, and they don't state it here, but in all of the solutions in the back of the book, we want to write our constant of integration in terms of some general initial conditions. So I'm going to add in here in terms of x naught, where x naught is some generic initial condition at 0. And then finally, use a computer generated slope field to sketch typical solution curves for the given DE and verify visually the stability of each critical point. So for this point, we're going to use Desmos Online. And so we'll flip out of here into a browser and we'll show how we're going to use that. All right, so to get started here, let's go ahead and solve for the critical points. I want to set this equal to 0. So I'm going to factor out my common factor of x and set it equal to 0. And here I see I get two critical points, x equals 0 and x equals 3. And what we would like to do is classify the stability of those critical points. So I'm writing little colons here, and then we will identify the stability. So in order to do that, let's draw our phase diagram. Let's plot our x values for our critical points, which are 0 and 3. And then pick some test points in here. Doesn't matter what they are, as long as you pick, for example, a number less than 0. So I'm choosing -1. A number between 0 and 3, I'll choose 1. And a number larger than 3, I'll choose 4. And I want to plug these test points, which I'll highlight in yellow, over into my function f of x. I'm going to use the factored one, but you could use the other one as well. And so then you just want to note here the sign of the derivative. So let's work with -1 first. If I plug -1 in, I get -1 times +4. That is negative. So I want to draw that arrow pointing to the left towards the negative x-axis. All right, so now let's plug in the critical point 1. That would be 1 times 2, which is positive. So I want my arrows to be pointing in the positive direction. And I'm going to draw 2 here so that they're at both critical points 0 and 1. And then finally plug in your last critical point 4. That would be 4 times negative 1, which is negative. So I want that arrow to be pointing in the negative direction. Okay, so this is our phase diagram. And we can read this phase diagram by saying, all right, at 0, my arrows are pointing away from my critical point. So my solution curves will move away from 0. That is unstable. And then at 3, my arrows are pointing towards 3. So my solution curves will converge toward that equilibrium solution. That indicates stability. All right, so we have identified and classified our critical points. Next, we'd like to move forward in solving this differential equation. All right, so this is a separable DE, and all of these are because T is not occurring in the differential equation. So all we need to do is divide that x times 3 minus x over to the left-hand side to get all of the x's on the left. And then, of course, the dt is by itself on the right. So what we're going to want to do here is for our x portion, we need to integrate by way of partial fractions. So I'm going to set up my partial fractions. Each of those are linear terms. So I'm going to slap an a and a b in there. And then we would like to solve for a and b. So I can equate the integrands of the x integrals. Then I can multiply through by the common denominator. So I'm going to multiply by x times 3 minus x. And that reduces this down to 1 equals a times 3 minus x plus b times x. Now we've seen this before, but here again, equality is equality for any x value. So let's pick convenient x values to solve for a and b. And the convenient x values are the roots of your factors, namely x equals 0 and x equals 3, which are just your critical points. So if x equals 0, what happens? The b term drops out and we get 1 equals 3a. So a equals 1/3. And if x equals 3, the a term drops out and 1 equals 3b, or b equals 1/3. So now we want to take those two values and we want to plug them in up top. So I'm going to pull those 1/3s out front and we get 1/3 of 1 over x plus 1 over 3 minus x dx equals the integral of dt. So now we can integrate directly here. We get 1/3 of the natural log of x. And then if you need to do a u substitution here, we're going to kick out a -1. So this is minus the natural log of 3 minus x. And that equals t plus c. Don't forget your constant of integration. All right, let's do a little bit of simplification. I'm going to multiply both sides by 3, and then I'm going to collapse those natural logs using the property of logs, that the difference of two logs is the log of the quotient. So this becomes the natural log of the absolute value of x over 3 minus x, and that equals 3t plus c. Here, where I only multiplied my t by 3, and I absorbed the 3 into my constant of integration. All right, I'm going to go one step further, and I'm going to apply the natural exponential function here. So I get x equals, or excuse me, the absolute value of x over 3 minus x equals e to the 3t plus c. And as is common, I'm just going to write that e to the c as the constant c. Now, normally I will um, drop my absolute values and put a plus or minus. So let me go ahead and just erase those absolute values and pay for it with a plus or minus. But here again, that constant is either positive or negative, and we would determine that based on initial condition. So I'm going to just absorb those plus or minuses into the C, and I'm going to leave this in this format. Now, this is certainly not written in explicit form yet. All right, we need to solve explicitly for X, but I recommend pausing at this point in your solution to solve for your constant C. It's going to save you some headache later on. So I'm going to make the assumption that X at time 0 is some X naught. All right, I don't know what that value is, but I'm just going to let it be X naught. So if I do that, then what I have is X naught over 3 minus X naught equals C e to the 0, which is 1. So I have now solved for C. And so my new equation, my implicit solution, is X over 3 minus X equals X naught over 3 minus X naught e to the 3t. Let's clean that up a bit. All right, so what I want to do from here is just solve explicitly for X. And it's kind of ugly, but you just have to get through it. So I'm going to multiply both sides by 3 minus X, and I'll distribute. So I have X equals a 3X naught over 3 minus X naught e to the 3t minus X naught over 3 minus X naught e to the 3t times X. Now remember, I'm trying to solve for X, so I want to move all of my X terms on one side. So I'm going to move this entire expression over to the left, and in the same step, I'm going to factor out that X. So what I get here is X times 1 plus X naught over 3 minus X naught e to the 3t equals just that single term over on the other side, 3X naught over 3 minus X naught e to the 3t. And then finally, I can divide through both sides by this expression here in the parentheses. So I conclude that X of t is equal to 3X naught over 3 minus X naught e to the 3t divided by 1 plus X naught over 3 minus X naught e to the 3t. I would absolutely give you full credit right here for your answer. If you wanted to simplify, you could multiply the top and bottom by 3 minus X naught just to get rid of those complex fractions. So again, this is an optional step, but it certainly makes your solution look more aesthetically pleasing. And so what we're going to get here is on top just a 3X naught e to the 3t. And on bottom, I get a 3 minus X naught plus X naught e to the 3t. So this is how the back of the book will write their solutions. But either one is perfectly acceptable. All right, finally, if you'll recall, let me scroll up here a bit. The last sentence here says use a computer-generated slope field to sketch typical solution curves for the given differential equation and verify visually the stability of each critical point. I do want you to include this on your homework, but I am expecting you to use some sort of website to help you generate this. So what I'm going to do is I'm going to include this sketch just down here in the corner. We don't need tons of room. So I'm going to draw a set of axes. And what I'm going to do is I'm going to sketch in the equilibrium solutions. So you'll recall that we had X equals 0 and X equals 3. I'm going to sketch those in red. and I'll label them x equals 0 and x equals 3. And the question is, what do all of the solution curves look like above and below those lines? So let me back out of here and open up my browser. And where I'm at is on Desmos.com, their slope field generator. Now, I want to emphasize one thing here. You'll notice here in box 1 that their derivative is in terms of dy dx. Our function in problem 4 was dx dt. So their y's are our x's. Make sure that you make that switch. So our function was 3x squared minus, or 3x minus x squared. I'm going to write that in terms of y. So let's back up. And I'm going to write this as 3y minus y squared. All right. So let me hide this here. And so you can see the equilibrium solutions. Hopefully everybody can see those horizontal dashed lines at 0 and at 3. And then you can see how the curves are sloping toward or away. So if we look from the top, our solution curves are coming nearly straight down. And then as we approach x equals 3, they start slanting toward it. And if you want to zoom in here, you can see a little bit better how they're sloping toward that equilibrium solution right there at x equals 3. I'll back out again. And then you can see in between the equilibrium curves at 3 and 0, they're sloping toward 3, but then kind of backwards to the left at 0, and then they're diverging away from 0 down below. So I'm going to take this slope field, and then I'm going to use it to sketch what the solution curves look like in that coordinate axis that we had on our notes. All right, so it looked like this. I'm going to plot these in black. They were coming down from the top and tending toward our equilibrium solution. And then they were coming from the left up and toward the right. So they kind of look like these wonky S's. And then they were diverging away from 0 down below. So this is all I'm looking for on your homework, is a quick sketch. You guys shouldn't be doing any of the graphing in terms of, plotting points and kind of doing a t-chart, anything like that. Just use that slope generator to look at these curves. And then you should check, does this make sense with what we said for our stability? So we had said that x equals 0 is unstable. Does that match what our graph says? So here's x equals 0, and yes, from left to right, as t is increasing, those solution curves are diverging away from 0. Conversely, if we look at x equals 3, from left to right, our solution curves are converging toward 3. So we see stability there. All right, so this is a nice double check to make sure that what you found earlier is matching graphically. On a quiz or an exam, I would not ask you to come up with the slope field and the sketches of solution curves. What I might ask you to do is, if I provide you the sketch, can you identify the stability? But I'll never ask you to sketch that curve because you don't have access to a slope field generator. All right, so that's problem 4. Problem 8 has the exact same instructions. Find the critical points, classify them using a phase diagram, solve explicitly for x, and then sketch typical solution curves. So let's begin by finding our critical points. No need to factor, this thing is already factored. We only get one critical point here, and that is at 3. Oops, not 0, 3. All right, and so let's go ahead and plot a phase diagram. And 3 is our only critical point. Pick test points on either side of 3 and plug those into that function. Now, this is a unique function because the outside is being squared. So that makes that 3 minus x, quantity squared, always positive, but then we have a negative out front. So it doesn't matter what I plug in, I'm getting negative values for my derivative. So then both of my arrows should be pointing toward the left, toward the negative direction. All right, so there's my two arrows. And then based on those arrows, I can see that I'm diverging away from 3 from the left and converging toward 3 on the right. So that means we are unstable or semi-stable. All right, so there's our critical point with its associated stability. Next, let's go ahead and solve explicitly for x. All right, again, these are always separable. So go ahead and separate your variables. I'm going to leave the negative over with the t's, but it is unimportant as to which side you move it to. So I have a negative dt. And this is a more pleasant problem because you could solve this by way of partial fractions, but you don't need to. You can just use a u substitution here. So u equals 3 minus x. Du is a negative dx. And so what we get is a negative u to the negative 2 du equals the integral of negative dt. All right, so I'm going to use the power rule. That becomes a -1, divide by -1. I get a u to the -1, which is a 1 over 3 minus x. And this equals a negative t plus c. Here again, let's go ahead and solve for c. So if x of 0 is some generic x naught, then c is going to be 1 over 3 minus x naught. So we can go ahead and plug that in. I have 1 over 3 minus x equals a negative t plus 1 over 3 minus x naught. And just to make my life a little bit easier, what I'm going to do is I'm going to get a common denominator to combine these two terms on the right. So this is a negative 3t plus tx naught plus 1 all over 3 minus x naught. All right. And then from here, I can reciprocate. And typically the book likes to factor out the t, so I guess you can do that if you would prefer. So that's an x naught minus 3 plus 1. But again, that's optional. Okay, and so now let's go ahead and reciprocate. That gives me 3 minus x equals 3 minus x naught over t times x naught plus 3. Oops, that's a minus. Plus 1. And then finally solving for x, I get x of t equals 3 minus that entire expression. All right, so here is our explicit solution. Again, we would like to plot those solution curves. So I will draw an axis. I'm going to plot my equilibrium solution in red. And I'll label that x equals 3. And then let's back out yet again and use Desmos to help us with the plotting. So let's go ahead and delete this. And whoops, equals. So we had a negative parentheses. Remember again, our x is Desmos's y. And then we want to square that entire term. All right, so hopefully you can see the semi-stability here. You can see that above that equilibrium solution at 3, the solution curves are coming about straight down, but then tapering off toward the right, so heading toward that equilibrium solution. But then below, we're coming from the equilibrium solution and diverging away and straight down. So let's go ahead and copy that over in our axis. So we're coming down and toward, and then from it, we're moving away from. And so again, this just confirms what we had found up above, that our critical point was semi-stable, and sure enough, our solution curves are converging above and diverging below that equilibrium solution. All right, we have just one more example here to finish off these notes. And this is just simply going to be looking at the solution curves and determining stability. So these are quite a bit quicker. It says use a computer algebra system or a graphing calculator to plot the slope field to determine the stability of each critical point. So before we start plotting, let's just identify the critical points. You can factor this just one step further. That difference of squares becomes x plus 2 and x minus 2. So our critical points are x equals 0, x equals 2, and x equals -2. And what we would like to do is classify the stability of those points. So here again, let's sketch our coordinate axis. And our equilibrium solutions. So we have 1 coming across at 2, 1 coming across at -2, and of course, 1 across the middle. So this is the t and x axis. All right, and so we just want to fill in the blanks in these 1, 2, 3, 4 sections above and below each solution curve. All right, so keep in mind our function is x cubed times x squared minus 4. We'll move back to Desmos and we'll type in our new function here. So y to the third times y squared minus, whoops, let's get back in there, minus 4. Okay, make sure we have it all in there correctly. It looks good. Now here, if you need to zoom in a little bit just to see what's happening, sometimes it helps. And it is kind of tough here to see, but it appears, let's maybe add some more grid points. Yeah, we'd like to see what's happening here above, because right now it just looks all equal. Let's see if we can add. I don't know if this is going to help or make it worse, but let's try it. Hmm. Oh dear. Let's restart here. So we had y cubed times, oops, y squared minus 4. All right, so we'll have to play around here a little bit, but we'll want to zoom in and add some more grid points here to really identify what's happening above 2, because it's unclear whether it's going to converge toward 2 or away from 2. And then we can see what's happening in the 2 middle strips. But here again, down below, we'll want to just kind of zoom in and see what's happening. So I recommend you add some grid points, but I don't want to do it here on the fly, to really identify what's happening with those solution curves on the top and on the bottom. All right. But your solution curves should look like the following. They're actually diverging away from 2 up above. And then again, we could kind of see the slope fields look like, whoops, excuse me, they looked like this, and then they looked like this. And so you can identify here that we're coming this direction. And that gives that kind of downward sloping. And then the opposite in between. All right, and then again, it was hard to see what was happening beneath -2. Those are diverging away from -2. All right, so then using these solution curves, we'd like to identify the stability of each critical point. So let's start from the top to bottom. X equals 2. You can see from left to right, all of the solution curves are diverging away from 2. So that would be classified as unstable. At 0, the solution curves are converging to 0. So that would be stable. And then at -2, again, same as at 2, they're diverging away. So that would be unstable. All right, so this is the classification of our critical points. So make sure you feel confident identifying the critical points and their stability. All right, that's all for section 2.2. Thanks for tuning in.